Hello everyone. Today we are going to talk about FSMs and Datapaths. Before we get into the details of FSMs and the Datapaths of the new chapter, I just want to give you a brief overview of what we have done up until now. So, starting from chapter 4, we start to see the combinational circuits where we can gather together the gates and implement a specific function based on the inputs coming in, and then we have got the outputs. Then in chapter 5, we introduced the clock, the feedback path, so we can use the storage devices and we can sequence the operations by using the storage devices, and we can implement a circuits with sequential elements in there. So we introduced the clock, so there will be a synchronous operations going through, and we can store 1 bit of information in these flip-flops. Then in chapter 6, we have seen how we can combine these flip-flops or the sequential elements together to form registers, the counters, and that kind of sequential elements together. Now, from chapter 4 to chapter 5, they were on the same level, which just included the storage devices and the clock. With the chapter 6, we have gone one level up as a hierarchical design procedures from the gate level to more a block level design. So we have gathered 4 bits of the flip-flops or the 8 bits so that we can implement a counter over there or a register. Now with this chapter, chapter 8, we are going into a system design level, so one level higher than what we have seen up until now. And the system design or the digital system design is one of the fundamental working area or the technology that is going towards in a system design. So what we have seen is all the foundation of digital system design up until now, and now we are going to introduce the state-of-art design of the digital systems. So to have these systems, to understand these type of systems, we actually need to divide these things into a manageable blocks, let's say, because you cannot define a complete large digital system with just a state table. It's really difficult, because the number of states that you will need or the inputs that you need to deal with, it's enormous. So to overcome these difficulties, what we generally do as a digital system designers, we divide these into modules, or we can say that this is a modular approach that we generally focus on. So what we do over here, the digital system we are designing, we partition them into modular subsystems, each of which performs some functions. So if you do remember, we have seen the registers, we have seen the counters, we have seen adders, we have seen multipliers, comparators, multiplexers, and so on. These, each of them are actually a modules. So they can be used in this modular approach, and we can use them as a subsystem to gather them together to have a larger digital systems. Okay, so when we talk about modular approach, this is what we are actually saying. So we have got a smaller systems or the subsystems, combinational or sequential systems, that we gather them together to have a large digital systems. So these modules are constructed from such digital devices: the registers, decoders, multiplexers, arithmetic elements, control logic, and so on. And these various modules are interconnected with their data paths and the control signals to form a digital system. Now, if we put everything together, the submodules or the modular approach, the interconnection, the control signals, we form the system itself. So I just want to draw a picture of this, and we can say that we have got a complete digital system, let's say. Okay, and in this system we have got different submodules that we need to have to implement special functionalities. Okay, and in these submodules we have got data and address passes, so they are talking to each other. So we are transferring data from one end to the other and so on. So we create actually a, let's use a different color. We actually create a data path over here. So you transfer from one to the other, you perform some combinational operation, then shifting out or shifting in, parallel loads and so on. This can also be all done in a data path. Okay, and to actually tell what its module is going to do and when it is going to do, we need to use another approach over here, or another module, which we call it control unit. Okay, so in general, all these combined together to have a digital system. Now, we are going to see how we can build a digital system, but first we understand the modules inside of it. So, data path, we have seen the individual modules like registers, adders, muxes, decoders, and so on. So we have seen all these together. We have seen in chapter 4 and chapter 5 together, or chapter 6. Now this is actually forming the data path. What we haven't seen is the control unit. So we know we can get the data from the input, we do some operation and we get the output. But with the control unit, we need something over there to tell when it is going to receive a data, when it is going to transfer the data, when it needs to add the data, and so on. So this is all happening in the control unit. So let's give a start with these slides and with the definitions. This is chapter 8 in the book, if you want to check it out. So digital system design, we have two main elements over there: modules, data path unit, and the control unit. And as we already said, in the data path we have got the processing logic, registers, the multiplexers, and so on. So the pipeline, the process data flows through the data path. So we got the data from one end, input it in, copy it to another register, do some arithmetic operations, move to another register, send it to the out. These are all together is called register transfers or micro operations. Okay, so we perform register transfer and micro operations in the data path. The control unit, which is the brain of this data path, it actually tells when it is to do and what is to do. So it derives a sequence of data processing operations performed by the data path. So it actually controls the flow of the data. So what we can say about the operations in a digital system, they're actually controlled with the timing signals. So that are the sequence, the operations in a prescribed manner. So the outputs of the control logic are binary variables that initiate the various operations in the system's registers in the data path. So information transfer from one register to another is an example of a data path unit. So for example, this is a simple notation of it. So this is actually telling us R1 to R2. It denotes a transfer of the contents of R1 into register R2. So that is a replacement of the contents of register R2 by the contents of R1. So this is a typical register transfer operation. So what we do, we send a control signal to determine when the operation is actually going to be executed. So that's why we need the control FSM. So let's open a new page. So in a typical digital system, so we have said that we have got a data path, and to control this data path we need a control unit. Okay, so control unit, it's actually sending these control signals to determine when the operation is actually going to execute and which operation. And data path is, let's say, okay, let's do the control unit part, and we also have the control outputs. It can output an output for something else as well, not just for the data path. And on the other hand, data pad itself, it's actually sending status signals. So it's actually sending out the status signals saying that, okay, I'm ready for the next transfer, or this is already transferred, I'm ready for the next control, and so on. And also it has got data outputs. Okay, and of course for the data path we need some data inputs. So these are all actually happening inside of a digital system, and we also have control inputs. Okay, so all these together are working in a digital system to perform the operations in a sequences, and Datapad is performing all the processing operations with the registers and the transferring and so on, and the control unit is controlling these signals when and what to do actually. So we'll do an example, and I'll try to show you how are these things are going to happen. But before we get into there, the control unit which we are talking in a digital system is a finite state machine, FSM. So this is actually known as finite state machine, which we can say that the outputs are the control signals for the register operations. And based on these finite states, because we are having a sequence of states, because of these finite states we call it finite state machine. So if we get in there, FSM is another name used for sequential circuits. The name comes from the fact that the functional behavior of sequential circuits can be represented using a finite number of states. Since control unit is made up of FSM, sometimes the word FSM is used. So rather than saying control unit, you can just say FSM as well. Now, we are going to see an example now how we can do some operations related with a specific example. So here is a block diagram given to us. We have got the control FSM with control input start and subtract. We have got data inputs 3 down to 0, so 4-bit inputs are going into the data path and 4-bit outputs coming from here. And we also have some control signals like reset, add or subtract, load R2, load R1, and so on. So when we do this kind of stuff, when we do this kind of designs, we normally want a register transfer operation to occur not with every clock cycle, but only under a predetermined conditions. So what we can say is, for example, let's say if T1 equals 1, then R1 is going to be R2. So this is a condition. So not just with the clock that we are going through the cycles, but we have some predetermined conditions over there. So what we can do, we can use these register transfer operations in different parts of the digital system to move out the register values into different one and then do some operations related to that. So for example, I'll show you a few examples related to this. R1 is R1 plus R2. So for example, this is a addition operation. We are doing an addition through the registers. So what we are actually doing is, this is R1, this is R2. We put together these into an arithmetic operation, and the value is stored back into R1. This is a typical operation of it. Or what we can do is R3 is R3 plus 1, which is just an increment operation. So R3 again with an adder over there, and we increment by 1, and the result is stored back in R3. So we can use these register operations to perform any operation through the data path. So let's get into the details of this example, and let's see how are we going to deal with add subtract example. Now with the add subtract example, in hardware, how do we perform addition? We use binary adders. So we can use a parallel full adders together for 4 bits or 8 bits and so on. And how do we perform counting? We can use counters, and for the shift operations we can use shifters. So for each of these operations we have some hardware related with that, which we already seen some of these in chapter 4 and 5 or 6. So the type of operations, the transfer operations through the registers, the copying data from one register to another, arithmetic operations, logical operations, and shift operations are all can be done in a digital system. So the first example, adder subtractor, is one of the most important example which we can understand how a data path is working together. So I will show you the data path. So this is a typical data path that we have got 2 registers, adder and subtractor, and we have got the carry for the register and some data lines going from one register to the other and so on. So how are we going to define a control unit or the control signals based on this data path is up to us. So control logic actually generates the signals for the sequencing of the operations. Now, if we look at it carefully, The control commands that we are going to produce by the control unit are the primary inputs, the status signals and the state of the machine. So the control sequence and the data paths of a digital system are specified by the means of hardware algorithm. And this hardware algorithm is a procedure for solving the problem with a given piece of equipment. So these are the equipments given to us, and we have to derive some state-of-art hardware algorithm to make this equipments to work together in a sequence. And I think this is the most challenging and the most creative part of digital design, is the formulation of hardware algorithms for achieving required objectives. Okay, so let's see how are we going to deal with this. The problem is here. Given the system and the below data path block diagram, derive the state diagram for the control unit FSM required to load two 4-bit numbers to R1 and R2. Then the addition or subtraction between them, depending on the status of their control unit, subtract input 1 for subtraction and 0 for addition. Note the other subtractor unit either adds or subtracts but cannot perform any other operation. And assume the FSM resets back to initial state if or when start is deasserted and reset is synchronous. Okay, so all the specifications are given to us on how to design a control unit because we know the data path over there. So I'm just going to divide this into micro operations. Now, if we look at the data path, so when we reset, okay, or let's start with the cycle as it's a synchronous stuff. On the first or 0th cycle, we actually do a reset. When we do a reset, we are actually clearing out the registers. So R1 is going to be 0. R1 is 0 and R2 is 0. So at the beginning, that's what we have. Then, on the first cycle, we are not doing reset, so we start to our operations. So the first thing that we need to do, we have to load the data input into R2. So we can say that, say a load instruction over there. What it's going to do, it's going to get the data into R2. So I'm just writing sequences, micro operations now. So then what we need to do, as we have got the first 4-bit number in R2, we just need to load the second number so that we can add R1 and R2. To do that, we actually need to move the value in R2 into R1. So how do we do that? We have to load R1, and what we need to do, we need to set R2 to have a new data. So that means on the second cycle, we do another load, but this time we need to load or copy the contents of R2 into R1, and we also need to have the new data in R2. Okay, so we copied the contents of R2 into R1, and we have got the new data into R2. Now, on the third one, we want to perform some operations. So that operation, it can be either addition or subtraction. So for addition, we can use 0 for addition. For subtraction, we can use a 1. So I'll say 3a over here. With 3a, we can say that we want to add R1 and R2, but we want to store it in R1 because of the structure of the data path is showing to us. When we add these things together, after the adder and subtraction operation, the value, the output will be stored in R1. So that's why I need to write this statement. R1 is going to have the value of R1 plus R2. Okay? Then, if we carry on, the 3b, it's going to be again R1, but this time, rather than having an addition, we'll do subtraction. How do we do subtraction in digital systems? We have to use the complements. So R1 is going to be R1 plus, how do we do the complement? Take the inverse of R2 and add 1. So this is going to give us the 2's complement. And we can do subtraction. So in the end, we are just using other over there, but we perform a subtract operation using the complements, which we already mentioned these in the previous chapters. So these are the micro operations that we need to consider for this data path. Now, the next thing that we need to consider is our inputs. What are they? So inputs for the control or the data path coming from the control unit, we need a start because we need to fire it up. So inputs, start. And what else do we need? We need the subtract, or we can say operation. Let's use operation, it will be easier. So these are going to come into our control unit because we need to press start externally so that our system starts to run, and we need to specify what kind of operation we want to do in that data path so that the control unit knows what it's going to do. Then we have got the outputs. So those outputs which are going in as an input to the data path, it's actually specified over here because these are the inputs coming from the control unit itself. This is coming from outside, data in. This is going to the outside, data out. But these are actually our control signals coming from the control unit. So what do we have over there? We have got add or subtract. We have got load R2. We have got load R1, and we have got reset. Okay, so they have to be there because as they are going in as an input to our data path. Now, using these information, we can actually derive a state diagram. Okay, so I'll just open a new page and we can go through this together. So how are we going to derive this state diagram? I'm just going to use a small pencil over here. So the control inputs, start and up, and control outputs. We have got add, subtract, load R2, load R1, and reset. Okay, so we will need these control inputs and control outputs. Now, these are going to happen in a couple of states, and we already, over here, we already have got these states. So these are the states that we are going to use. So first we do reset, then we load data into R2, then we load data into R1 and the R2, then we do 3A for R1 plus R2, then we do 3B for R1 minus R2, and then we go back or wait or whatever it is. So now let's see how these states are going to be transferred into a state diagram. So if we start with S0, now with S0, maybe I need to draw a bigger because we'll need a bigger space over there. With S0, we want to do a reset. So what will be the output of the control unit? Let's say this is the order of our outputs as we have that written over here. So first add is going to be 0, or subtract because we are not going to use that, so that will be 0. And load R2 has to be 0, we don't want to load anything. Load R1 has to be 0, we don't want to load anything. But the reset has to be 1 because we want to reset the data path first. Okay, so to do that reset, we have to put the reset output to be 1. So this is the first part of it, and over here we can say that start input is deasserted, so it's 0. I'll just say S for start. Okay, and whenever it's there, we are just not doing anything and we are just waiting over there. Then we can do S1, and that is actually when start is asserted. So when start is asserted, the first step that we need to do over there, we need to, maybe I can show you here. So we have done the reset, we initialize it. So on the first one, R1 is 0, R2 is 0. That's done in state 0. Then in R1, we need to have the data in R2. So that means we have to load R2 to be 1. Okay, so add and subtract, we don't care, but we use 0 over there. We don't want to set anything. Load R2 has to be 1 because we want to load something into register 2. Load R1, we don't want to transfer that to R1 at the moment, so that has to be 0, and the reset has to be 0 as well. So we have got the start, but we have to say that if start is deasserted, we have to go back to the reset. When we are in state 1, if the start is again asserted, so start is still asserted, we need to go to state 2. So in that state, what we need to do, we need to copy the R2 into R1. To copy R2 into R1, it has to follow this path. So the value that we have got in the first state has to be transferred into R1. So that means, how do we do that? To do that, it's going to be R2 plus 0, so that we get R2 value over there, and that will be actually stored in R1. Okay, so that means the add operation has to be 0 because we want to perform addition operation with 0, because we have got R1 as 0 as we have reset it. Then load R2 has to be 1 because we want to load the new value in there, and we also need to copy the previous value to the R1, so we have to load R1 and reset to be 0. So that's our second state. Again, if the start is deasserted, we have to go back. Now, the next thing that we need to do, we have separated these 3A and 3B, so R1 plus R2 will be A. So if we want to do an addition, we have to do one state, and for subtraction another one. I'll just say state 3 over here. So again, start is asserted, but now we need to consider the subtract operation input as well. So the add subtract is going to be, or the operation, it's going to be 0, right? So we can say that op prime. So opposite of the operation. So when it is 0, it will perform the addition. So the outputs over here, again, addition, we need to use 0. Do we need to load anything to R1? R2? No, it has to be 0. Do we need to load anything to R1? Yes, because the result of this operation has to be stored in R1. So we need to have the load signal to be 1. So that has to be 1, and the reset is 0. So we perform addition operation. On the other hand, again, if the start is deasserted, it goes back. But we need to have S4, which will perform the subtraction. So let's take this out. So S, and we have got op inputs over there. So now, what do we need to do? We need to do subtraction. So add subtract should be 1. Do we need to load anything to R2? No. Do we need to load anything to R1? Yes, the result of addition or the subtraction, and the reset is 0. So we have loaded our S4 with the necessary information that we need. Then we need to have another state which is not reset, which is not doing anything else, so the whole state. So we can create S5 over there. Okay, and of course this is going back when start is deasserted. With the S5 we are just doing nothing, so everything is 0, not loading, not addition or subtraction, not resetting. So we can actually go there when start is asserted, okay, and when start is deasserted, we have to go back and start again from the reset. Okay, and if start is asserted over here, we just wait over there. So now you can see that we have derived some kind of state diagram that defines the controls for this data path. So the first step, we load, we reset everything. So R2 is 0, R1 is 0, as you can see. Then we load, we initialize R2 to be 1, so we can load something in there. So data in comes in. Then in the third step, we need to copy R2 into R1, as R1 is 0 over there. So 0 plus R2 is going to give us R1 over there. So whatever we have got, it will be copied down to R1. Then the new data will be stored in R2. So both of these has to be 1 at the same time, and this has to be add operation. So that's why we have got that part 0, 1, 1, 0. Then if you want to perform addition, we have to set that to operation to be 0 for the input, and start to be asserted. So we are doing addition. We don't need to load anything to R2, but we need to load to R1 because the result has to be stored over there, and reset needs to be 0. So then if you want to do a subtraction, we have to have another state where we do a subtraction, but the op is now in the original form, not complemented. And we are not loading anything into R2. We are loading into R1 the result, and reset is 0. Again, start is asserted. If in any case start is deasserted, we have to go back to the reset state. And the last state, S5, we are not doing any operation. We are just holding the values over there forever until S is deasserted again, and we reset the system, start a new arithmetic operation. So this is how we can see a data path and use the information on the data path to derive a control unit. Now we are going to see the timing waveforms related with this data path. Now, the control unit design, the timing waveforms, we have got the clock which is going to run, and we have got the subtract. In our case, it's a op that we have used. So we use start and op. They use start and subtract. It's the same thing. Reset is active low, so it's high most of the time. So it has to be low to be resetting. Load R2, R1. They're all zeros at the beginning. Add is 0. Data in is A, and R2 is 0. And other subtractor 0 plus 0 because we don't have anything in there. So that is state 0. So everything is initialized. It reset the registers. We have got zeros, so the operation having in the adder is 0 plus 0. Next, we carry on. So we specify the data that we want to have some operations, and we specify the additional subtraction operation that we want to perform based on these data inputs. Now, the thing is, when the clock runs, we are going to see the changes over these inputs and the outputs of the control unit. So now, as we have got the subtract and start for our control unit inputs, we are ready to run. So the next thing that we are going to see now is we need to load R2 because we have done S0. Now we need to load R2. So what we need to have R2 to be 1, and we need to know that reset needs to be low. So when we start on the first cycle, reset starts to go down and R2 will start to go up. So that means we are loading R2 with the data A over here. Okay, so this is what we are going to see. Now, as you can see on the next cycle, as R2 is 1, we loaded A data into R2. Okay, and what is doing the other subtractor part is A plus 0, which is A, which is just an addition because add and subtract is 0 over there. Then on the next cycle, what we need to do, we have to copy the content of R2 into R1. So that means that's why R1 is going to be 1 and R2 needs to be staying 1. So now on the next clock cycle, R1 is 1, R2 is 1. And as you can see, as we have got A plus 0 as A, that will be transferred into R1. So we have got A on R1. and in the same time, as R2 is also 1, the next data in is going to be transferred into R2. So we have got A, B, which is transferred into R2, and A is transferred into R1. Now the next operation that we are going to have is A plus B. So as add and subtract is 0, we deassert the R2 because we don't want to store anything in there. We are not accepting any new data. And R1 has to store the value of the result of A plus B. So that's what's going to happen. So A plus B will be stored in R1. As we are not loading anything over there for the next clock cycle, we'll just have A plus B as an output of R1. Okay, now start was deasserted over there, so we are not doing any operation, and the reset was asserted. So R2 and R1 are going to be zeros again. As you can see, they're both zeros because of the reset. Now on the next clock cycle, we are loading the new data in. So new data is C. Okay, and also the subtract is going to be, or the operation is going to be a subtraction. So we have to assert this add subtract control signal. And as we are carrying on, but before we do that, we loaded R2 with C. We have to load R1. So we have to copy that C into R1, and we have to load R2 with D. So that's done. So we have got D and C over there. Then after that, we are ready to assert the add subtract 1. So that's going to be 1 so that we can perform C minus D operation. So, and we got C minus D stored in R1. So this is the timing waveform explaining how these operations are going to run. Now, the thing is, as we have got the timing waveform, as we have got the state diagram, now we need to derive the state table of this state diagram. So we have to define the table based on these states, and we have to define what will happen using these inputs and the outputs. So I'm just going to open a new page and go through that. Now, probably you're not going to see the states, but I'm just going to show you the state diagram over here. So at least you will have an idea. So this is our state diagram that we have drawn, and based on that, we have to draw our state table. Now, we have got state 0 to state 5. So I'll just say, I'll change the pen because we need to write tidy. So present state, then we have got next, and we have got output. So these are all the things that we need to consider. Present state. So for the next, actually, oops, let's do it this way. We have got based on the inputs, so start, subtract, when it is start is 0, we don't care about subtract, so we can just say X. So start, something wrong, and nope, not organized. Hang on, this is really important, so I have to be really careful on how to design this table. So present is there. Then we have got start and op. We have got start and op and start and op. So this is actually when start is 0, operation is X. When start is 1, operation is 0. And when start is 1 and operation is 1. And we also got the output add or subtract. I hope I can fit everything there. L2, no, it's not gonna fit in there. It's really difficult to fit everything into one page, I'm afraid. So present, start, op when it is 0x, then start op when it is 1, 0, then start op when it is 1, 1, and we have got output, which is add or subtract, L2, L1, reset. And these are all next state. Okay, so I think that will be better. So now we have got state 0, state 1, state 2, state 3, state 4, state 5. So based on that, we are going to derive what's going to happen. So when we are in state 0, if the start is 0, we don't really care what is happening with the op. It's going to be S0. Again, if we are in S1, it's not updated yet. Okay, so that's S0. If we are in S1, start is 0, that means state is S0. And S2, start is 0, that means S0. State 3, start is 0, that is also S0. 4, start is 0, that is also S0. And 5, start is 0, that is also S0. So for each of these, as you can see, whenever the start is 0, we don't really care about the op or the other signal. We are just going back to state 0. So when start is 1, operation is 0. We have to go through start 1 and then that one. So when we are in S0, next state is S1. When we are in S1, next state is S2. And I think this is not updating quite fast. So when we are in S2, if the start is 1 and operation is 0, we have to go to S3. And when we are in S3, if the start is 1, operation is 0, we have to go to S5 and stay in S5, because when we are in S4 and operation is 0, again it's S5, and when we are in S5, again we stay at S5 as the start is 1. So when start is 1, operation is 1. Up to there, I think they have got the same thing. So that's going to be S1 and S2, because it has to go through those two. Then when as the subtract or the operation is 1, we have to go to S4. And when we are in S3, if start is asserted but operation is 1, again we go to S5, S5 and S5. So these are all S5s. So the outputs with S0, as you can see, it's 0, 0, 0, 1. So we just say 0, 0, 0, 1. When we are in S1, it's 0, 1, 0, 0. S2 is 0, 1, 1, 0. S3 is 0, 0, 1, 0. S4 is 1, 0, 1, 0. And S5 is 0, 0, 0, 0. So we have got the outputs as well. Okay, so as we have got all the necessary information for the state table, the next thing that we need to consider is to do a state assignment. So each of these states has to be assigned to a binary variable. So if we go from the slides, so this is a state table that we have got. It's similar that we have it over here with the state names. So there are a couple of approaches. We can use our ordinary binary assignment, we can use gray code, or we can use one-hot state assignment. So from here, I'm just going to show you that if we use binary state assignment 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0, for example, you can think about how many flip-flops do we need to use and so on. So with this type of binary assignment, if we use it, the minimum number of flip-flops that we need over here, as we have got the 5 variable and 4 variable, 3 variable k-maps, we need to design a sum of product form. We have a lots of things to do over there. So the resources that we need to use is quite large. So what we can do is we can use one-hot state assignment rather than binary assignment, which may be probably give us the minimum number of flip-flops that is necessary. So rather than having 3 5 variable and 4 3 variable k-maps for these type of state tables, we can just use one hot state assignment, and we can derive all the necessary outputs for our circuit. So I'm just going back to our whiteboard. I'm just gonna use the rest of this table, and I want to do one hot state assignment. So for the one hot state assignment, based on the states, we have got A, B, C, D, E, F. So we have got 6 states over there. So each of these is going to represent one of them. So A, B, C, D, E, and F, as you can see. Then from there to there, again we have got the output add and subtract, load 2, load 1, reset, and for these ones we have got 0x, 1 0 and 1 1 for start and the operation. So with the one hot state assignment, we just need to tell which one is turning on one at a time, like we have done it. So let's say state 0 is going to be 0 0 0 0 0 1. Then state 1 is going to be 0 0 0 0 1 0, which is E. Then D is going to be 0 0 0 1 0 0. Then C is going to be 0 0 1 0 0 0. Okay. Then B is going to be 0 1 0 0 0 0. And A is going to be 1 0 0 0 0 0. So we have got all the combinations with the one hot state. So all we just need to do, we just need to replace each of these states with these values. And let's take this down. Right, so with state 0, as this is F, it's going to be 0 0 0 0 1. So all these state zeros are going to be 0 0 0 0 0 1. 0 0 0 0 0 1, 0 0 0 0 0 1, 0 0 0 0 0 1, and it goes. So we have got S0 replaced with 0 0 0 0 1. So that's F actually. Then S1 is represented on these cases, in this case, which is E. Okay, so which is 0 0 0 0 1 0. So S1 is represented in those two conditions, and those two are going to be 0 0 0 0 1 0 and 0 0 0 0 1 0. So we have got S1 on those two conditions. Then we have got S2. S2 is going to be 0 0 0 1 0 0. So S2 are on these two conditions. So 0 0 0 1 0 0 0 0 0 1 0 0, and those are represented over there. S3 is over there, which is 0 0 1 0 0 0, and we don't have any other S3. We have got S4, which is 0 1 0 0 0 0, and the rest is S5, which is 1 0 0 0 0 0, 1 0 0 0 0 0, 1 0 0 0 0 0, 1 0 0 0 0 0. And the outputs are same as before, so 0 0 0 1, 0 1 0 0, 0 1 1 0, 0 0 1 0, and 1 0 1 0, and 0 0 0 0. So we have got the one hot state assignment state table, and now we have to derive the expression for it. So how are we going to read? If you do remember from the previous chapter, we just need to find out where each of these ABCDs are going to happen. So let's start with A plus. So A is 1 0 0 0 0. So 1 0 0 0 is happening in all these conditions over here, as you can see. So 1 0 0 0 is happening over there. On this point, start is 1. Okay, so operation is changing, so we don't need to write that. So we can say that S should be there, and it's happening in these A, B, so A, B, and C, as you can see. A, B, and C. So that means that's going to be A or B or C. And that's the expression for A. For B, it's 0, 1. Let's use different color again. It will be easier. Okay. Let's use red. So for B, what we have is it's 0, 1, 0, 0, 0. So state 4. It's over there. And that is happening when start is 1 and operation is 1. So we can say that start and op, and it's actually happening only when D is 1. So we can just say D over there. Then we have got C. For C, let's use a different color. C is 0, 0, 1, 0. So that is actually over here. Okay. So again, C next is when start is 1, operation is inward, and it's also happening at D. So this is going to be D as well. And we have got ABC, we have got DEF as well. So DEF, D is over here, 0, 0, let's change the color, 0, 0, 0, 1, 0, 0. So those two are having D. So start is 1. And op is changing. And this is happening where it's E. So it's just start and E. And for E, next, so E is 0, 0, 0, 1, 0, 0, which is over here. And that is where start is 1. And it's just F. And the last one, F is happening on all these conditions over here. So where start is 0 and the rest is changing, so we can just say start bar over there, and that will represent F next. And for the output, we just need to check when the output is changing over there. So for example, add and subtract, it's there, and that is coming from B. So that is B actually. I don't have any space over here, but as this is add and subtract, that has to be B. For load R2, we need to have these two, which is D and E. So these two are D and E that we need to consider. So D or E has to be there. Then for L1, it has to be B or C or D. And for reset, it's just F itself. So if you use one hot, we'll have these outputs, and these are the next state expressions. Okay, and based on that, you can draw the circuitry that you need to have for this control unit. So I hope this is clear. If you have any problems, please do study, and you can ask me during the question and answer session. So the couple of more slides related with the data path design. Data path is designed by identifying temporary storage required in digital system and coming up with a combinational logic between consecutive registers, and the nature and the size of the temporary storage and the combinational logic depends on performance, power, size, cost, and potentially other design constraints. So register transfer operations or micro operations provide information on the data path. So in this example, we have seen how we can use the approach of deriving a control unit for a data path defined. And we'll do a couple of examples and exercises related with these.